Thanks very much.
Yes, Rory, please, you can start.
Thanks. So today I'll be speaking about a generalization of multilinear maps in a general context in category theory. And multilinear maps have been generalized before. One well-known such generalization is the generalization to the setting of commutative monads. So it's well known that we get a generalization of the notion of bilinear map for a commutative monad. And also, interestingly, there was a generalization of bilinear maps provided by Banaszewski and Nelson in the context of concrete categories over set. And in this talk, we'll go to a much broader setting, and in particular, we'll make use of multicategories, also known as operads or colored operads. So to begin with, we'll start off by considering the data for what's called a symmetric multicategory. A symmetric multicategory V has a class of objects. So in this respect, it's a bit like a category. We have objects. A category also has morphisms. In a multi-category, we have morphisms of the following form. Rather than going from a single object to another object, these morphisms go from a list of objects, x1 through xn, to another object, y. And we want to be able to compose these morphisms. When in a multi-category, we can compose morphisms in the following way. If we have a morphism G from a list of objects y1 through yn to an object z, then if we have a bunch of further morphisms, n of them, fi, going to the object yi, then what we can do is we can plug in these morphisms into the inputs of G, so to speak, and compose these morphisms in the following way to obtain a morphism G of f1 through fn, which goes from the entire list of objects obtained by concatenating the various objects xi, concatenating the n lists of objects that are the inputs of the fi. So we concatenate all those, and we get a morphism valued in z from there to z. And we also want to have identity morphisms for each single object. And in a symmetric multi-category, we also have what we can call permutation actions that do the following. Given a morphism f from x1 through xn to y, and a permutation sigma on n letters, we can, in a sense, permute the inputs x1 through xn and obtain a morphism f dot sigma, which goes from the permuted list of objects to the same codomain y. And we ask that these data satisfy several axioms, including associativity and identity axioms, and also a number of axioms pertaining to the permutation actions. Okay, so symmetric multi-categories generalize symmetric monoidal categories in a certain sense, because every symmetric monoidal category V may be regarded as a symmetric multi-category. In other words, we get an example of a symmetric multi-category with morphisms obtained in the following way. We look at morphisms F from the monoidal product of several objects x1 through xn to y in the given symmetric monoidal category V. And in this way, we can regard symmetric monoidal categories as symmetric multi-categories. In a kind of converse direction to a certain extent, Elmendorf and Mandel have shown that every symmetric multi-category V embeds into a symmetric strict monoidal category, which we're writing as V tensor. And the objects in this monoidal category are lists of objects from the original multi-category V. So we have an embedding of V into a symmetric monoidal category V tensor, which we'll refer to in this talk as the symmetric monoidal envelope of V. Given a symmetric multi-category V, we can consider categories enriched over this symmetric multi-category V. So a V category or V enriched category C has objects, a class of objects obc, and rather than directly asking for morphisms, we ask for hom objects. Script C A B should be an object of V, the object of morphisms from A to B. And this we have for each pair of objects A and B of C. And we ask for composition morphisms of the following form. So we have a morphism here in V from the list of two objects, script CBC and script CAB, to script CAC, providing composition given by a morphism in V. And we also want identity morphisms. These we express also as morphisms in V, where the domain is the empty list. So we have morphisms of this form valued in script CAA. And we ask that these data satisfy associativity and identity axioms. So this directly generalizes the usual notion of V enriched category enriched in a monoidal category. This is a generalization to the setting of multi-categories. And here we happen to be using a symmetric multi-category, even though this definition doesn't depend on that. So in this talk, we'll actually make use of a concept that's somewhat more general than V-enriched categories, because one issue is that V itself isn't in general a V category. If V is a closed symmetric multi-category, then V itself will be a V category also. But here we're not assuming that V is closed, so V itself isn't necessarily a V category. But so then what is it? And what we'll describe is a concept that's more general than V-enriched categories in such a way that it includes also V itself and also includes various other things like categories and so on. So to accomplish this, oh yeah, sorry, I forgot about the last point here, which is simply that if we take V to be the category of sets, then of course set-enriched categories are the usual locally small categories. Generalizing V categories, as I mentioned, we'll introduce the following concept. A V multi-graded category C, so these will be a kind of generalized V-enriched categories. By definition, we'll define this to be a V-tensor hat enriched category, where this V-tensor hat is the presheaf category, V-tensor op to set. So the presheaf category on V-tensor, recalling that V-tensor is the symmetric monoidal envelope of V. And we'll equip this presheaf category with its deconvolution monoidal structure. But when we spell out the data for a V multi-graded category in this sense, explicitly a V multi-graded category C has a class of objects, obc, and it has a notion of morphism, but they're morphisms in context in a certain sense. So these morphisms go from an object A to an object B, objects of C, but they're morphisms in a context, as you can see, x1 through xn. This context consists of a list of objects of V. So in the domain, in a sense, we have a list of objects of V, but then we have a single object A of C. And we have substitution along V-tensor morphisms. So if we have a morphism in the symmetric monoidal envelope, a morphism alpha going from a list of objects y1 through ym to a list of objects x1 through xn, then we can pull back the morphism f along this morphism alpha to get a morphism of the following form. F dot alpha then goes from y1 through ym, semicolon A to B. So we're changing the context by pulling back along a sort of context morphism, a morphism alpha in the symmetric monoidal envelope. And we want to be able to compose these generalized morphisms. So there's a composition required, which we can describe, and identity morphisms also, and we ask that these data satisfy certain axioms. So this is an unpacking of the notion above, which we're calling a V multi-graded category. And the great thing about V multigraded categories is that they not only generalize V categories. So first of all, every V category C is a V multigraded category. How does that take place? Well, we need to take our V category and describe what the V multigraded structure that it carries would be. So we need to say what a morphism F in context X1 through Xn from A to B would be. And we can define this to be simply a morphism as we've indicated below the line, F going from the list of objects X1 through Xn. In V, a morphism from that list of objects to the Hom object, script C, A, B, because that's an object of V. And making this definition, we are able to give C the structure of a V multigraded category. So first of all, certainly every V category is an example of a V multigraded category. And we can think of these V multigraded categories as generalizing V categories, but V multigraded categories also include V itself. So V itself carries the structure of a V multigraded category in a kind of very straightforward way where, you know, the morphisms in a given context from an object to another object, they're essentially just morphisms in V. So V itself is a V multigraded category, but it's not necessarily a V category unless V is closed, a closed symmetric multi-category. So reviewing part of what we've said, V embeds into a symmetric monoidal category V tensor, the symmetric monoidal envelope, and then that symmetric monoidal category embeds into a larger symmetric monoidal category V tensor hat, the day convolution presheaf category. So consequently, we get a change of base functor in a certain sense, going from VCat, the category of categories enriched over a given symmetric multi-category V, into V tensor hat cat. But this V tensor hat cat, this is the category of V multigraded categories. So in particular, this sends each V category to that V category regarded as a V multigraded category, but also we can now, by this functor, regard V functors as examples of morphisms between V multigraded categories. These we call V multigraded functors. And now we come to one of the main definitions of this talk. We're going to generalize the concept of multilinear map to this setting where we have a given V multigraded category C. So in particular, we can keep in mind the case where C is a V category. We'll also ask for a functor down to V from C. So let G be a V multigraded functor from C to V. So for example, if C is a V category and if V is closed, then G would be a V functor valued in V. Given these data, so one thing to note is that, you know, C itself is not yet, it's not a multi-category. It has more so the status of a V enriched category. But what we're going to do is describe a notion of multilinear map in C. So to do that, suppose we're given a list of objects A1 through AN in C and also another object B of C. Then we'll define a G multimorphism F from the list of objects A1 through AN to the object B to consist of the following data. First of all, we'll ask for a morphism, vertical bars F, down in V, going from the underlying list of objects in V to the underlying object G of B. Okay, so this is similar to what we would ask for a multilinear map, but we want to say now that the map is linear in each variable separately. We want to express that it should be a morphism in C in each variable separately. And how can we do that? Well, here, G, the functor G, is not necessarily even faithful. So we'll have to actually ask for some further data that witness this, linearity in each variable separately, so to speak. We'll have to ask for further data that witness that f is a morphism in each variable separately. And so we ask for the following data for each j between 1 and n. We ask for a morphism in C of a certain form. And you can see that it's a morphism in a sense from AJ to B in C, but it's in a certain context that appears on the left. And that context consists of the objects GA1 through GAN, except with the jth element of the list deleted. So we're deleting G at AJ. We ask for a morphism of this form, and we want it to witness that vertical bars f is a morphism in its jth variable. So we say that we require that the following diagram commute. So the requirement is that when we apply G to f super j, throw that down to V, we get the morphism on the upper edge of the triangle. And we want that to be the same as what we get by applying the permutation on the left and composing with the underlying morphism in V. This gives us a very general notion of multilinear map in this categorical setting. Let's take a look at examples. So we can specialize, for example, to the case where V is the category of sets, and we can look at just an ordinary category script C and any given functor G from C to set. And we can look at these G multimorphisms, in particular, the case where we just have two inputs, so to speak. We have a list of two objects, A1 and A2. We obtain the notion of G bimorphism, F, from A1 and A2 to B. And this consists of a given function, vertical bars F, from G at A1 times G at A2 to G at B. And then two further morphisms, families of morphisms actually. So on the left, we have morphisms f sub y super 1 going from A1 to B, and we want a morphism like this for each y in G at A2. And this should witness that, that the given map is a C morphism in its first variable for each fixed element y of G of A2. And similarly, we ask for a family of morphisms from A2 to B, one of these given for each element x in G at A1. And we ask that these morphisms in C be sent by G to the maps vertical bars f blank y and vertical bars f x blank respectively. Let's take a look at some examples. So we'll consider a given functor from a given category C to set and look at the notion of G bimorphism F from A1 and A2 to B. If we take C to be the category of real vector spaces with its forgetful functor to set, then we obtain the usual notion of bilinear map. We can also take the C to be the category of topological spaces with its usual forgetful functor to set. And then, as the notion of G bimorphism, we obtain the notion of a map that's continuous in each variable separately. So these notions arise from monoidal structures on RVEC and TOP, but here's an example that doesn't arise from a monoidal structure. We can look at simply the category of groups, not necessarily abelian, the category of groups with its forgetful functor to set. And the notion of G bimorphism in this example gives us the notion of a map that's a group homomorphism in each variable separately. These examples all involve faithful functors, but we can also look at examples where the functor G isn't faithful. So in that regard, we can consider the objects functor from cat to set, for example. And as the notion of G bimorphism for this non-faithful functor, we obtain the notion of sesquifunctor, a functor in each variable separately. Perhaps more basically, we can look at the forgetful functor from graphs to sets, the objects functor from the category theorist category of graphs to set, or in fact, any of several other categories of graphs. And we can look at G bimorphisms in this context. And they are morphisms F from A1 box A2 to B, where box is the box product of graphs. So we get these various examples as instances of G bimorphisms, and in particular then, these are instances of G multimorphisms. An example where the base of enrichment isn't set is the following, where we take V to be the Levier half-line. Then V categories are Levier metric spaces. And so in particular, let's look at, take C to be the metric space R squared with the usual Euclidean distance. And then we'll take G, the functor G, to be in this setting, the 2 norm. And so this gives us a V functor from C to the base of enrichment, 0, infinity, op. And we can look at what G bimorphisms are in this setting. What are they? A G bimorphism in this setting is simply given by 3 points in the plane, A1, A2, and B points in the plane, such that the following inequations are satisfied. And so if we can look at an example, for example, if we take A1 and A2 to be these points, then we have a bimorphism, G bimorphism to a point B, if that point lies in the intersection of the indicated circles. All right, and this brings us to our main theorem, which we'll state in the following very general context first and then specialize it. So I've proved the following theorem: let V be a symmetric multi-category, and let C be a V multigraded category. So for example, C can be any V enriched category. And we'll suppose we're given a functor G from C to V, a V multigraded functor. And then I've proved that when we look at the underlying ordinary category of C, that's C naught, and I proved that C naught underlies a symmetric multi-category script CG. So C in this way carries the structure of a symmetric multi-category CG, in which the morphisms are these G multimorphisms that I've described. And in particular, we can apply this theorem in the usual setting of enriched category theory, where we take V to be a symmetric monoidal closed category. And in this case, we can apply this theorem to any given V functor C from any V category, any given V functor G from any V category C to the base of enrichment V. And so this shows then that the underlying ordinary category of script C carries the structure of a symmetric multi-category where the morphisms are these G multimorphisms, generalizing multilinear maps. And we can specialize this further to arrive at the following result for ordinary categories, that if we just take any given category C and any given functor G from C to set, so a set valued functor, it doesn't have to be faithful, just any given set valued functor, well then we deduce that C underlies a symmetric multi-category, CG, in which the morphisms are these G multimorphisms that I've described. And that brings me to the end of the talk. Thanks.
Thank you, Rory, for this interesting and clear talk.
Thanks.
Is there any questions I would ask first here in person? Yes.
Thank you, Rory, for the talk. I wanted to ask if you know if there is any relation with the framework for generalized multi-categories of Crudwell and Schulman. Is this more general, perhaps?
Good question. So the framework of generalized multi-categories. So of course, here we are simply working with essentially one particular instance of the notion of generalized multi-categories. So here we're working with symmetric multi-categories, which would be a particular instance of that. And so indeed, it's an interesting question to ask, you know, does any of what I've done here generalize to a setting of generalized multi-categories rather than simply symmetric multi-categories in particular? So Interesting question. I don't really have any definite answer to that. Thanks.
Thank you very much. So if I have something very quickly, so because the symmetry is not easy to drop the symmetry here.
Yes, exactly.
Okay.
That's a good point. That here I really use the symmetry because
I see.
if we go back to certain earlier elements of the talk, I'll try to keep this very brief. Basically, when we go to defining the notion of G multimorphism here, just as an example of where symmetry shows up, basically you can see at the bottom of the screen that on the left we have an isomorphism. That's actually in the symmetric monoidal envelope V tensor, but we have a permutation being used there where we kind of take this G of AJ and move it into the jth spot. So here we're really using the symmetry. And so I think that this crucially uses the symmetry. That's one notable point. Yeah. Thank you.
Yeah, thank you so much. I enjoyed a lot. Thanks.
Thanks.
Thank you, Rory. More questions? See if there is something online.
In the
Does
chat.
CG itself naturally have the structure of a V multigraded symmetric multicategory?
Yeah, V multigraded symmetric multicategory. Yes, excellent question, and I do believe that it does. Like in particular, you know, this going in this direction, we find that that if certain limits exist and so on, then CG will become a V enriched symmetric multicategory as well. So yeah, indeed, this is an important point that one can go further to describe CG as not just a symmetric multicategory, but in fact a V-enriched multicategory if certain limits exist. And as you're saying, the exact sort of generalization of that to the setting that we're working in would require that, you know, CG be CG carry V multigraded structure as well and be a V multigraded symmetric multicategory. So I do believe that that works. I haven't completed the proof of that, I don't think, but it should work. Yeah, thanks very much.
Okay, thank you, Nathaniel, for your question. Thank you, Rory. We must go to the second lecture.
Thanks very much.
Thank you.
Thank you.